So you're going to hear that from now on. Whenever I pause it and start it, it's going to say, we stopped and then we started. Be careful, alert everybody, alert the media. So if you can't see the boards and stuff, somebody might want to change the lighting. I could do it, but I want to just kind of pick up right where I left off on Friday. So you have the box against the wall. And this problem itself wasn't that it was so terrible, but some of you had some difficulty with the mathematics of it. Some of you had difficulty just figuring out where this force went. And that part bugs me a little bit, but I'm going to get over that. We measured our angle relative to a normal. So this is the angle and this is the force. And the hard part about this problem was people not recognizing that the frictional force changes direction depending on how much you apply your force against the object. If you push too hard, the frictional force will be downwards to try and prevent the box from sliding up. If you don't push hard enough, the frictional force will be upwards to prevent the box from sliding down. So once you realize that, you realize you actually have two different questions. They're linked together, sure, but they're two different questions. So let's say that we're pushing too hard in this circumstance. So the frictional force will be downward to try and prevent the box from going upwards. Now, this force is still got to be broken up into its components. And since the angle is here, those components are going to be F cosine theta and F sine theta. Questions about that? Now, several students have come to me and said, look, I don't know what we're solving for in these problems. And I can respect that a little bit because it just looks like a whole bunch of letters. But at this moment within the problem, that shouldn't matter to you. Your job isn't to worry about that now, although it would be nice to know where you're going. You don't have to know that here. You just have to follow along with a set of steps that will get you to something that you hopefully could use later. So right now, all you should be doing is resolving your forces into their components, setting up two one-dimensional problems. And that's what we're doing. Net force in the X direction and net force in the Y direction. The boxes, we don't want them to slide, so they should be equal to 0. And that's all you're working towards right now, is to come up with a relationship that you might be able to use to solve for your answer. So in the X direction, I'm going to have normal equals F cosine theta. Those two have to be in balance. And in the Y direction, I'm going to have F sine theta has to equal friction plus mg. Those two have to be in balance. Now, none of this solves my problem, which is what is my value for F? And looking at these two, there's no way to eliminate a variable between them. There's nothing I can solve for in one of these equations and eliminate it in the other. That leaves me with an answer that only has what? M, theta, and perhaps G in it, maybe mu. Because if I try to eliminate, say, theta between these two equations, I'll be left with an equation that has normal force and friction, and those can't be in my answer. If I try to eliminate force between these two, well, that's ridiculous. That's what I'm solving for. How hard do I have to push against the box? So if you reach a point like this where you're not sure where to go next, perhaps you're not bringing enough information into the problem. And it should be clear anytime you see, coefficient of friction, perhaps something about the coefficient of friction has to be used in the course of solving your problem. Some third piece of information that perhaps you haven't had a chance to use yet. Now, I'm not saying that this will solve the problem either. I am saying that you have a better chance if you use all the information that's given, as opposed to only some of it. Even right now, if I was to strip away everything that's on the screen and just be left with what we have developed friction is less than or equal to mu times the normal force. We're pulling that because there's a mu given to us in the problem. Based on my geometry, I have normal equals F cosine theta. And I have F sine theta equals friction plus mg. You are tasked with trying to find the minimum or maximum force that you can apply to the block to keep it from sliding. You have three relationships here. When all else fails, start substituting. It's the way to go. Start eliminating variables that can't be in your answer and see if you can finally get yourself to a point where you have something that is a function that has the variables you're allowed to have in your answer. Look, we are more likely to get problems like this than anything with numbers. Numbers make it easy because with numbers, you can kind of weed out what's been given. Here, it just looks like alphabet soup and it's harder. And I respect that that can be troubling to you, but that doesn't change the fact that that's what the expectation is. Especially in a problem like this where you are given a threshold. What is the minimum? What is the maximum? That's a suggestion that you'll have to use your inequality. So substitute. Substitute into your inequality. F sine theta minus mg less than or equal to mu f cosine theta. Now, I know from years and years of experience that if I can use the equation for friction, I will be simultaneously eliminating friction and normal force in my equation. You don't know that because you have limited experience. But in your notes, that might be a valuable piece of information to write down. That bringing the equation for friction into your problem helps you bring together the x direction and the y direction in such a way as to eliminate friction and normal force from your expressions. Now, solving this may or may not be trivial to you. You still might not know what comes next. So I'll remind you, and you might want to remind yourself by putting this into your problem. Circle what it is that you actually need to have by itself. Remind yourself what you're looking for. I'm looking for how hard can I press against the object. That's F. And try and find a way to combine that, to bring that by itself, to solve for it. And you know how to do that. You've had years and years of algebra. So at this point, I really don't want to tell you how to do algebra if I can avoid it. Just do the things you've spent years learning how to do. Boy, that's messy handwriting, Mr. Shelton. Yep, sure is. Now, this isn't the only answer. There are two answers. But this is how you find the first one. Now, if I want to find the next one, I need to change where that is. And that's not a lot, but it is a little bit that I have to do. So I'm going to grab and move that force to the other side real quick. I'm going to see how that changes what I've written here. And it doesn't change it very much, but it does flip what side it was on in this equation. I mean, that's where it changes, right? And then when I come back over here and look at how it's going to change it here, it's going to change this part still. So I might need an extra step. And now I can substitute. So that I'll get mg minus f sine theta is less than equal to mu f cosine theta. I still have the same job though. I still have to get f by itself. That's still what I'm trying to do. And now, so this is going to give me the minimum value because my f has to be greater than this. And this is going to give me my maximum value because my f has to be less than this. Now, I don't know where you guys are in the whole, I understand this, I can do this, I did this on Friday, or I have no idea what you're doing scale, but I intend to find that out tomorrow, first 10 minutes of class. There's no subtext there, right? You're having a quiz, first 10 minutes of class tomorrow. It'll be at least this level of difficulty. And it's to tease out who can do this and who can't. It's always easy to understand it when Mr. Shelton is doing it. Always. Because it's not because I'm smarter than you. It's because I've been doing it all day and last week and for the last 25 years. I make up the problems. I'm just a magician. All I have to do is stay one day ahead of you. So here's my new magic trick. And by magic trick, I mean, let's see if you can do this. If this were the quiz tomorrow, would you be successful? I hope so. I think this one's easier than the last one, but we'll see. I've got an inclined plane, angle theta that I can adjust. I'm going to place a box on that plane. Like so. Box has mass m. And there's a coefficient of static friction of mu s between the box and the ramp. What's the maximum angle I can lift the incline without the box sliding? You folks hear that at home? What is the maximum angle I can lift the incline without the box sliding? So that's your question. I'll give you 5 minutes. 5 minutes to bang it out. Talk with each other. Check your work, because one of you is going to be telling me how to do this. You guys at home, would you like to work in breakout rooms? Have a friend to talk to? Get the embarrassment out in the small room and then bring it to the big room? All right.
I'd like a breakout room.
That's good. I was doing that. So there you go. So look, the answer is theta has to be less than equal to the inverse tangent of mu. That's the answer. Now, if this were a quiz, are you passing? Because if you are, you're in fine shape. If you're not, you have a problem that we need to try and diagnose. Because tomorrow, I guarantee it's not going to be this easy. So part of what we need to figure out is, where's your disconnect? Are you able to get a Newton's law formula for both the x and y direction? Are you able to get that far? Are you not able to get that? Where are you having difficulty? And I can't dictate that. It's always going to look easy when I do it. This problem starts with the same thing we've done for a while here, which is there's 3 forces acting in this system. I'm going to have weight downwards, normal force perpendicular to the ramp, and the only direction friction could possibly act is up the ramp to keep the box from sliding down the ramp. Do you have those things, Sean? Because you're going to need that. There's no way around it. And then I'm going to decide on a coordinate system, a way to analyze the problem, a way to break the problem up into one-dimensional pieces so I can study it. The fact that the system doesn't move means that my best bet for solving this problem is to break it up so it's lined up with the normal and the frictional force. That way I have the most number of forces along an axis as possible, which is going to require that I take the weight and break it up into 2 components, mg cosine theta and mg sine theta. By doing that, I'm basically saying that these two components make up for the force that was there before. This is the first law problem. I didn't state that. I didn't think I had to, but I don't want the box to move. So the net force in the x direction has to be 0. That means mg sine theta has to equal friction. The net force in the y direction also has to equal 0, which means what? Well, it means normal force has to equal mg cosine theta. Well, what do I do now? I want theta in terms of this other stuff, but I can't have normal or friction in there. Well, it's a coefficient of friction problem. I was given the coefficient of friction. Perhaps I should work this into my problem. This will eliminate friction and normal force. So that's where I should go. So mg sine theta is less than or equal to mu mg cosine theta. I think we're pretty much done now, aren't we? I mean, you do your work, you're going to get tan theta has to be less than or equal to mu. That's really the end of the problem right there. You can solve it for theta. I typically don't leave inverse tangents in my functions, but they said solve for theta, so that's what you should probably do. Yep.
Can you explain why you put your components there? Back on the free body diagram.
Yeah, I could. So let's, I'm just gonna make it nice and big so that there's less ambiguity. The weight has to be directed straight down. So I wanna make it a different color. The normal force has to be directed in this direction. We lined up the coordinate system to be lined up with the normal force. So the normal force and the positive y are lined up together. That's purposeful. And friction is lined up specifically to be in the positive x or negative x direction. Now, do you know why this angle is theta?
I mean, that's where I put it.
That's not what I asked. So you need to be able to come to grips with why when I am looking at this particular example, an example of any one of these, why this angle is the same as that angle. Now, there's a number of ways to consider this, but the simplest way is consider what happens if I try to make this angle smaller. This has to go to 0 when this goes to 0. But the easiest way to dictate it is whatever line you have that lines up with the normal, that's where your angle goes. That way you always know. Now, that being said, deciding where sine and cosine go is no longer a matter of your choice. This is mg. If I wrap an angle around, if I wrap a triangle around my angle, that means drawing a component down the y-axis. I'm drawing the adjacent side first, I always do. And then lining it up with the end of this vector, turning and drawing the other component so that it hits it from a perpendicular. This is the adjacent side, this is the opposite side. So this has to be cosine, and this has to be sine. Try another one? We're gonna try another one. I'm not leaving the realm of difficulty. I'm gonna keep this one about the same level of difficulty. So you're in a car. This is a car. You ever hung something like off the rear view window of your car? I'm sorry, off the rear view mirror of your car? When you accelerate forwards, this thing swings backwards. So I want you to imagine I have an object that is, you know, tied to a string on the rear view mirror of my car. When I accelerate forwards, it swings backwards an angle theta. So we need to measure that theta from the vertical. Object has mass m. I would like to know the acceleration. What is the acceleration of the car in terms of theta? I'll let you have m, g, and theta in your answer. Try this one. Not a whole lot different than the last one. I want the acceleration of the vehicle in terms of the angle. You guys at home want to talk it out with somebody?
Yes.
All right. You guys in class, of course, can do the same. All right, let's get back to it, folks, because we're going to run out of time otherwise. Bell rings in like 4 minutes. The biggest thing you had to realize here is that the box is accelerating with the car. So the box has an unbalanced force acting on it. The inexperienced tend to be looking for something that's not here. There's only two forces that act on the box. When I go through my list of forces, there's definitely weight downwards, but the only thing in contact with the box is tension. Those are the only two forces that act in the system. With that being said, the tension has to not only lift the box and keep it from falling, but also accelerates the box to the right. So there's one component of the tension that's got to be balanced in the y direction, and another component of the tension that is unbalanced in the x direction. So free body diagram. But even if you didn't know that, a lot of people add forces here that just don't exist because they were in the last problem or they're in other problems that were similar. But there's just these two forces. When I set up a coordinate system, I'm going to line it up in the direction of the acceleration. That's where my priority should always be. So the positive x direction is the direction of the acceleration. I believe that it's going to move along with the car to the right and accelerate to the right. By consequence, that's the positive y direction. This is also theta. Has to be. Do I need to explain that? Alternate interior angles. So let's go back to 9th grade or 8th grade. This was the vertical line before. This is the vertical line now. This blue line is the cable, and it's a straight line that cuts through two parallel lines. Because of that, alternate interior angles must be equal. Geometry gets you every time. Now, focusing on what I have here, T cosine theta has to equal mg. I'm looking directly at this component. And this component has to be T sine theta. T sine theta is unbalanced. So the net force in the x direction has to equal ma. So T sine theta equals ma. Now, I have two equations. that both have two unknowns, theta and t. Need to get rid of it. So you can solve for t in one and plug it into the other. That's not how I'm going to do it, though. I'm going to divide the two equations. Or you can divide the same thing on both sides of an equation. T cosine theta is the same thing as mg. So on the right side of the equation, I'm going to divide mg and just get a over g. And on the left side of the equation, I'm going to divide t sine theta by t cosine theta and get tangent theta. So the acceleration is g tan theta. All right, guys, that was the bell. Practice tonight. We're going to do this first 10 minutes of class tomorrow for a grade.
Mr. Shelton.
Yeah. I'm listening.
Could you explain which one, like, how did you decide which one to set to equal MA?
Could I explain which one I what?
Set, like, why did you decide the X to equal MA and the Y to equal 0?
Okay, so I've got something in my car. If I'm in my car and I'm traveling horizontally along the road, which direction am I accelerating? Am I accelerating up and down, or am I accelerating horizontally?
Horizontally. Oh, I see. I see. Okay.
Does that make sense?
Thank you. Yes.
You're welcome.
Have a nice day, Mr. Shelton.
You too. Bye, guys.